Okay, let's dive into this explainer and learn exactly how to play the examiner's game to master your syllabus. Welcome to what we like to call Casino Royale high-stakes answers. Look, when you walk into that Cambridge Computer Science exam room, the tension is palpable. The stakes are incredibly high, the clock is ticking down like a literal time bomb, and every single mark you can grab is a chip on the table. But here is the massive secret that top-tier students know. This isn't a game of chance. There's no luck involved here. It is a game of strategy, precision, and knowing exactly what the house, in this case, Cambridge, is looking for in your answers. Whether you are building your foundational knowledge right now in the 0417, 0478, 0983, 0984, or 2210 syllabuses, or you are facing the absolute ultimate test in the 9618 AS and A-level exams, the rules of the house remain surprisingly consistent. Today, we're going to deconstruct the ultimate high-stakes topic, the one that literally makes or breaks your programming logic, the declaration of variables. We're going to show you exactly when to hold your facts, when to fold your inefficient code, and when to go all in on analytical depth so you can walk out of that exam room with top marks.
Now, what's really interesting about this quote from a senior Cambridge examiner is that it proves a point a lot of students get wrong. Examiners aren't out to get you. They actually want you to succeed. They are telling us directly where students are bleeding marks on the paper. They don't want to fail you, they want to reward you for clear, logical thinking. But you absolutely have to understand their playbook first. You see, the principal examiner reports consistently highlight that the declaration of variables isn't just about regurgitating what an integer or a string is from a textbook. Honestly, anybody can do that. It's about demonstrating a total mastery of fundamental principles. They want to see that you understand memory allocation, local versus global scope, and how to choose the absolute perfect data structure for a weird, unfamiliar context that they've thrown at you. When an examiner says this is the most misunderstood area, what they mean is that candidates treat it as a throwaway first step rather than the critical theoretical architecture of their entire program. Think about it. If your foundation is weak, your whole algorithm is going to collapse.
So, the crucial point we need to make here is that this specific strategy is tailor-made for mastering variable declarations in your Cambridge examinations, with a real laser focus on the highly demanding 9618 AS and A-level syllabus. The academic benchmarks for this level are intense. They require highly logical, structured reasoning. The assessment framework explicitly prioritizes your analytical depth over just superficial breadth. This means the days of just memorizing a glossary of terms are completely over. To hit those top assessment bands, you must exhibit a connected, conceptual understanding that you can seamlessly transfer to completely unfamiliar, complex business or scientific contexts provided in the exam paper. Every single time you declare a 1D array, a custom record, or even just a simple counter for a loop, you are making a deliberate design choice. And today, we are going to decode exactly how to communicate those choices to the examiner so you extract maximum marks.
So, here is our roadmap for today's explainer. We'll start with the exam challenge, cover core principles, dive into the procedural framework, learn about winning with method marks, highlight top examiner warnings, and finally, evaluate your algorithm.
All right, let's jump straight into Section 1, the exam challenge.
Let's start by looking at why students struggle so much with multi-step algorithmic calculations and lose points right out of the gate. You know the feeling. You open the past paper, let's say it's a notoriously tricky paper like Code 9713, and you're hit with this incredibly complex scenario requiring a custom software solution. The panic sets in almost instantly. Do you use a 1D array, a linked list? How on earth do you initialize the tracking variables for this specific problem? This exact moment is where the separation between an average student and a top-tier student happens. The challenge isn't just knowing how to code, it's about decoding the specific command words hidden in the prompt and structuring your answer to match the exact mark scheme Cambridge has locked away. This brilliantly illustrates the two most common traps we see time and time again. Look at this split screen. On the left, we have Alex. Now, Alex is smart. Alex has memorized the entire textbook, but when asked to declare variables for, say, a hospital database, Alex completely overloads the answer with raw computer science facts. We're talking listing every single data type available, detailing the specific byte size of each, but completely failing to provide any analysis of why specific data types are needed for this hospital database. Alex writes a massive paragraph, eats up 10 minutes of exam time, but scores very little. On the right, we have Sam. Sam is terrified of the ticking clock. Sam rushes the answer, immediately writing out pseudocode declarations without actually reading the command word requirements. Sam declares an integer to store a customer's phone number. That's a classic, fatal mistake. If you use an integer for a phone number, the system drops the leading zero, corrupting the data. Plus, Sam completely misses the requirement to justify the choice. Both Alex and Sam are leaving massive chips on the table because they lack analytical depth or fail to demonstrate connected understanding.
Moving into Section 2, Core Conceptual Principles. But before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get into the strategy.
Okay, we need to completely rebuild how you approach these answers. We are transitioning from just wildly throwing code at the page to applying a rigorous, structured methodology that examiners are literally desperate to reward. According to Principal Examiner reports, top-performing students build their theoretical architecture on these exact 3 pillars. First up, precise definitions. You must know exactly what your data structures do and state it clearly. Second, causal relationships. This is a big one. If you declare a local variable inside a while loop instead of a global variable at the start of the program, what is the causal effect on memory allocation and program logic? You absolutely must articulate this. Third, cross-topic connections. Guys, this is the absolute goldmine for high marks. The reports constantly highlight that candidates who reference cross-topic connections achieve significantly higher grades. For example, linking your choice of variable declaration to its impact on network transmission speeds or secondary storage efficiency shows incredible depth. To consistently apply these pillars, you need to use the PEL framework. That stands for point, evidence, explanation, link. Make your point about the variable. Provide evidence from the prompt scenario, explain the technical justification, and link it back to the overarching goal of the algorithm. If you structure your answers this way, the examiner has no choice but to give you the marks.
And this brings us to the ultimate problem-solving framework for algorithmic thinking and step-by-step decomposition. Deconstruct, solve, evaluate. Before you write a single line of pseudocode declaring your variables, you must deconstruct the problem, take a breath, identify the given information, break that terrifying complex scenario into logical bite-sized steps. Then, and only then, do you solve systematically, making your declarations. Finally, and so many students skip this, you must evaluate and check for reasonableness. For instance, if you declared a variable to track a user's age, did you set a boundary condition to prevent negative numbers or someone entering an age of 999? This is what we mean by making justified recommendations. It's a completely closed-loop system of analytical perfection.
Let's look at Section 3, the procedural framework. Now we're moving to the execution phase to see how a standardized sequence can totally transform your answers. We are taking those core principles and turning them into actionable, repeatable steps. Think of this as your computer science success blueprint. Look, when you are sitting in the exam hall and the pressure is mounting, you do not want to rely on random inspiration. You want to rely on a cold, hard procedure. A procedure is immune to stress. By strictly following this 5-step sequence, you guarantee that your data structure selection and code implementation are rigorous and efficient. Step 1, identify key elements from the prompt. Are you dealing with whole numbers, characters, Boolean flags? Step 2, apply relevant principles. If the prompt mentions a list of 1,000 employee names, immediately apply the principle of array data structures rather than declaring 1,000 individual string variables. Step 3, execute analysis with clear working. Write out your declarations clearly, explicitly showing the scope. Step 4, verify results. Do a quick mental dry run. Do these variables actually cover all the data needs of the problem without wasting space? Step 5, present in the appropriate format. Use standard Cambridge pseudocode or the specific programming language requested, ensuring your syntax is absolutely flawless. When you do this, watch as your disorganized, rushed thoughts transform into a highly structured answer that turns the examiner's red pen marks straight into green check marks.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome back. Let's dive into Section 4, Winning with Method Marks.
Now it is time for an interactive workshop. We're going to focus on data extraction from binary representations and complex problem breakdowns. I want you to imagine a really complex computer science data source on the screen in front of you. Maybe a trace table that has gone completely wrong, or a massive block of raw binary data that needs to be declared, parsed, and manipulated. The clock is ticking down from 60 seconds. You have to scan that data, extract the core trend, and figure out the computational logic. It is intense, right? Your heart rate goes up. So let's address the absolute biggest fear in the exam room. Executing a multi-step calculation perfectly, carefully declaring all your variables, beautifully setting up your nested loops, but then messing up the final logic condition or miscalculating the final output.
You look at the final answer, you know it's wrong, but the invigilator calls out, pens down. Have you lost all 8 marks for that question? Does your grade completely tank just because of a simple arithmetic mistake or a minor syntax error at the very end of your code?
The answer is no, and let me tell you, this is the ultimate safety net. Examiners actively want to give you points for your process, so never, ever skip showing your work. This is the method mark strategy. Cambridge Principal Examiner reports explicitly state that algorithmic thinking requires step-by-step decomposition. If you declare your variables correctly with the right data types, if you write the correct iterative loop structure, if you initialize your counters properly, you are going to pick up method marks for each and every one of those systematic processes. Even if your final output is totally incorrect, you might still score a solid 6 out of 8 marks just for showing clear logical working. So I repeat, never just write down a final answer. Show the examiner every single step of your deconstruction and code implementation. Make it impossible for them to give you 0.
Let's test this with a speed writing challenge. Take a moment to mentally extract the core trend from a complex scenario and structure a perfectly linked explanation using that Peel framework we talked about. Imagine a scenario where a computer system monitors temperature sensors in an automated greenhouse. You have 30 seconds. Ready? Go. Point. Declare an array of real numbers. Evidence. The temperature data provided in the prompt requires decimal precision. Explanation. Using an array allows for efficient iterative processing through a for loop to calculate daily averages. Link. This fulfills the system's core requirement to track continuous environmental changes accurately without losing data precision. Boom. That is exactly how you apply the Peel framework in an instant. That is how you secure maximum marks before the timer runs out. No fluff, just pure, targeted analysis.
All right, let's move to Section 5, Top Examiner Warnings. Let's look directly at the Principal Examiner reports to uncover the critical mistakes that destroy grades every single year. We've talked a lot about what to do, but now we absolutely must talk about what not to do. The examiners compile these reports annually, and honestly, it is like they are handing us the cheat sheet to the entire exam. If you just avoid these most common pitfalls, you automatically elevate yourself above the vast majority of candidates. Avoid these 3 classic traps, especially ignoring boundary conditions, and your algorithmic thinking will immediately stand out as A-star quality. Trap number 1, using the wrong algorithm for the context. Please, don't use a highly complex bubble sort when a simple linear search on a declared array is all that is actually required by the scenario. Efficiency matters. Trap number 2, and this one is massive, forgetting to check boundary conditions and edge cases. When you declare a variable to hold a student's exam score out of 100, what happens if the user accidentally inputs 101 or -5? If your code doesn't account for those edge cases with validation checks, you lose marks immediately. Trap number 3, providing generic textbook answers. If the question is specifically about a hospital database, do not give me a dictionary definition of what an integer is. Nobody cares. Tell me that the integer is used to securely store the unique patient ID to ensure relational database integrity. Context is literally everything.
Bringing us to our final core section, Section 6, Evaluating Your Algorithm. Finally, to hit those highly sought-after higher-order assessment objectives, you must prove to the examiner that you can evaluate and compare alternatives. It is not enough to just write an algorithm that technically works. A grade C student writes an algorithm that works. An A-star student writes an algorithm, then actively turns around and criticizes their own work, compares it to alternative approaches, and meticulously justifies why their specific variable declarations and data structures are the absolute most efficient choice. By systematically addressing time complexity, space complexity, and edge cases, you justify your recommendations and secure the highest possible marks. Let's look at this evaluation table here. Time complexity. How fast does your algorithm actually run? If you declared inefficient variables inside a nested loop, your time complexity explodes exponentially, and your system performance drops. Space complexity. How much memory does your program consume? If you declared massive global 2D arrays when simple local variables passed by reference would suffice, you are wasting precious memory space, which the examiner will heavily penalize in an evaluation question. Edge cases. How robust is your solution when faced with extreme, unexpected data inputs? Addressing these 3 metrics explicitly in your extended answers demonstrates that profound connected conceptual understanding that the Cambridge syllabus essentially demands from its top scholars.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing.
Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here.